All right, good morning, everyone. So we're going to start a new unit today on optimization. And one of our main motivations is that we've now seen that we have some optimization problems like the one we saw in logistic regression that we can't solve on paper. We need to attack them numerically. So we'd like to know how to do that. We know that some of these things are implemented, but I'd like to know a little bit more about how they're implemented and how we can do this ourselves if we wanted to. So we're going to focus on gradient-based techniques. So we just have to start from the beginning and talk a bit more about the gradient. So I know we've talked about it a little bit, but we'll talk about it some more now. So the gradient, so again, our objective is to minimize some cost function j. We want to find the lowest point. And one of the things we know, this is an unconstrained optimization problem, so there's no constraints on W, and we're going to assume that j is smooth. So in that case, we know that the minimizer occurs at a point of zero gradient. So we've used that several times. We use that for our least squares minimizer derivation, for example. But there's a few other things about the gradient that are useful. For example, the gradient tells us the direction of the maximum increase as well as the slope at any point. So this picture here shows the gradients with little arrows. So if you're right here, you can see that the gradient arrow is pointing this way. So that would be the direction you want to move if you want to increase the value of the function. And then the length of the arrow shows the steepness at that point. And so when you look at this is going to be the bottom because the gradients are pointing away, and this is the top because the gradients are pointing to it. You can see that the gradients there have zero magnitude, so the slope is zero. So those are, the important things about the gradient. And again, we know that the gradient exists if the function is smooth, and that's going to be our assumption in this unit, or at least for now. And then we'll see that there's another thing we can do with the gradient is we can use it to linearly approximate a function. So we'll talk about that in just a moment. Okay, so how do we define the gradient? So we're always going to focus on a scalar valued function that we're trying to optimize. We're never going to try to optimize something with multiple costs. So it's a single scalar valued cost. However, the number of parameters, there might be many of them. So if the parameters we're trying to optimize over are in a vector, then we have a vector valued gradient. So that would be this case. So we're trying to optimize this vector of coefficients W, and then the gradient will have the same shape as W. So the gradient is defined as the partial derivative with respect to the first, second, third, and so on, all the way so we get to the partial derivative with respect to the last component in Wj. But we also saw some examples where the parameters that we want to optimize are arranged in a matrix, right? So we saw that in regression with multiple targets, or multinomial logistic regression with multiple k greater than 2 classes. So there we want to optimize over a whole matrix, and we can actually define the gradient in this case too. The gradient will be defined, it will have the same shape as W, and it's again just the partial derivatives with respect to each of the components of W and arranged in the same way as W is arranged. Okay, so no matter what, the gradient always has the same dimensions as the input. Later on in the course, we'll be talking about tensors, which are like 3, 4, 5 dimensional objects. Matrices would be 2-dimensional. So those things you can define the gradient again in the same way. Whatever the shape of W, the shape of the gradient is the same. Okay. So let's just do a really simple example where we have parameters are just a 2-by-1 vector here, and the cost is just excuse me, a polynomial in these different coefficients. And so what we want to do to compute the gradient is we just take the partial derivatives of the cost with respect to the first one, which, as you can see from here, is going to be 2 times W1 plus 2 times W2 cubed. And then we take the partial derivative with respect to W2. So the first term goes away, and we get 6 times W1 times W2 squared. Now that we know those partial derivatives, we just stack them as into the same shape as W, and that is the gradient. It's very easy to code this. In Python, we make a little function here that evaluates the gradient, and it's actually going to return both the cost and the gradient. So first we write the cost, where we compute the cost itself, this, and then we compute each term in the gradient, and then finally we stack those terms in the gradient into a NumPy array, and we return both the cost and the gradient here. Later, when we want to evaluate the gradient at some new point, we create a new point, and then we just call this function, and it returns for us both the cost and the gradient, and here we can plot them, or print them out. Okay, so as usual, when we deal with arrays, we're going to use NumPy arrays for our gradients. All right, so here's a slightly more interesting example. So what we're doing over here, if you look at this, you can see that here are some targets, yi, and here is a model that's an exponential model of the data. So you have your features, you're scaling them by b, exponentiating that, and then scaling that by a. So we want that this is as close to yi as possible. We're going to use the mean squared error, or the RSS loss. And so the two parameters we want to optimize are a and b. So we stick those into our vector w. Then we compute the partial derivatives of this j with respect to a and then b. So using the chain rule, we take the partial with respect to a. So first we can move the derivative inside the sum. So then we apply the derivative to this. So by the chain rule, you get 2 times this. And then we have to apply the derivative to the interior. So that's going to be, the y doesn't have an effect, but we look at this, the derivative of this with respect to a is just going to be minus times that exponential. So that's where we get this expression here. And then we do the same thing with respect to b, and the gradient looks very similar up until the point where we have to take the gradient of this, and then when we take the gradient of this term, we get this term times xi. And so that's where we get this. Times minus xi. Okay, so finally we have our two partial derivatives, and then we just stack them together into this vector. The code is pretty similar to before. Just to make things a bit more explicit, we first unpack the vector into a and b. Then actually, we want to try to code this in an efficient way. We don't want to repeat the same numerical things over and over. So if you look at these two components, you can see that they share some similar terms. They both have this. So let's just compute this thing once and then use it twice later. So we're going to call this the y error. So it's going to compute this for all the different i's, and those are going to be stacked in this vector. And then, actually that appears here too. So once we have that, in order to compute j, you can see we just need to take the sum of y error squared. Actually, it looks like this is missing a 1/2. There should be a 1/2 there. So times 0.5. Okay, and then for this gradient with respect to A, we can see we have y error, so we can do a pointwise multiply of that with this second term, and that's what's happening here, y error times numpy exponential of minus bx, and then that's going to give us a vector, and then we just want to sum the components of that vector, so we can do that with numpy sum. We have something similar for the second part. We again can use y error, and then we just have to make this other part. These are all pointwise multiplies. This is the entire vector x, the entire exponentiated vector here, and so on. And when we're all done, we just stack those two partial derivatives into our gradient vector, and we return both. And then as before, if we want to evaluate this, we can create some data, just make some random y's and x's. These are both 100 points in vectors. And then we set some arbitrary parameters for w, and then we can evaluate the cost and the gradient at those points, and we find that they happen to take these values. Okay, so hopefully this is all pretty straightforward. Any questions so far? All right, so let's turn to the next idea, which is how can we use gradients to approximate functions? So first we're going to look at the simplest case, scalar input function, and then we're going to look at more complicated cases of vector and matrix input functions. So in the case of a scalar input function, so J just has a scalar input and a scalar output. So for example, on the right, the J could be this red curve. And so actually, this should be W, according to the notation on the slide. And what we'd like to do is we'd like to approximate this function at a particular reference point. And that reference point we'll call W0. It happens to be the origin in the picture. So one way we can write the function is through a Taylor series. And a Taylor series, this is an equality. So we're saying that the function at any point W equals the function at the reference point, so this is just a constant, plus a linear term, and this looks at the slope at the reference point, and then the deviation of W from the reference point. And then there's many, many other terms in the Taylor series, but we're just going to collect them all into this notation here, which says that all the other higher order terms together are at most a constant times this W minus W0 quantity squared when W0 when this W minus W0 is small, is when it's close to 0. So that's what they call this big O notation. So this big O notation here informally means at most a constant times epsilon squared when epsilon is close enough to 0. And there's a more technical definition if you've taken a real analysis course, then this will be familiar epsilon delta kind of notation. There exists positive constants c and delta such that the function of epsilon is always less than or equal to c times epsilon squared for all epsilon between 0 and delta. Okay, so it's kind of a mouthful, but that's the official meaning of this big O. Basically, we're using it to say there's an error to this first approximation, and the size of the error is approximately the size of W minus W0 squared, roughly speaking. Okay, so the way we can use this now is we're going to focus on the first part. But instead of writing it as an equality, we're going to write it as an approximation, and we're going to leave out this term. So this, when we want to have an equality here, we need it, but when we leave this out, then this equality turns into an approximation. And so this is known as the first order Taylor approximation of the function j at this reference point, omega naught. And according to the picture on the right, this would be that blue line. So if you want to approximate this red curve and you want the approximation to be best at the reference point and the approximation should be linear, then it's going to be this line. It touches there exactly, it's tangent there, and you can see it's quite a good approximation when you're close to there, but as you get farther away from the reference point, the approximation gets worse and worse. And so that's what this is quantifying. Here we're not quantifying it exactly, we're just saying it's good near the reference point. Okay, so again, we are approximating the function by a linear function in the neighborhood of the reference. And of course, what this is, this term here, this is the slope of the original function at the reference. So it's just the slope right here. And then this would be the intercept in this case, slope and intercept. Okay, so that's how we can use a gradient to do an approximation. And as we'll see, there's some nice uses of this as we go forward. Any questions on what we're doing here? Okay, so the next thing to do is to redo this for the case of vector input functions. So in this case, we have j. Again, it always returns a scalar output, but now the input is a vector of d parameters. So we're going to have another reference point. We're going to call it w naught. And then if we look inside it, we'll see like w naught 1, so on, all the way to w naught d. And what we'd like to do is once again look at a first order Taylor approximation of this function at the reference point. So following what we did before, we start by writing the function according to its Taylor series. So this is an equality. And when we look at the Taylor series, we see a constant term, which is the value of the function at the reference. And then we have a linear term, or you could say a sum of linear terms. And now because we have multiple inputs, we have to take multiple partial derivatives and we have to multiply them times their scalar deviations of that coordinate from the reference. So on the previous page, it looked like this, but we didn't have the sum because we had one parameter. Now we have many parameters, so we just sum over their individual linear terms. And finally, we have our big O term. So we have all the higher order terms in the Taylor series approximation. We're saying that their size is at most a scalar times this. This is the squared Euclidean norm of the error vector difference, or you could think about this as, if you want to think about it in terms of a sum, you could say that this is a sum over I of wi minus the reference point. Actually, I should probably use a j to be consistent. Okay, so we have a sum here, and now we have a sum here as well. Okay, is everybody with me here? So this is a Taylor series, but it's the Taylor series when you have multiple variables. And now we just want to rewrite this in a way that carries a little bit more meaning and generality. So the first thing to recognize is that this is just the jth element of the gradient vector. So we can write it like this, the jth element of the gradient vector. Over here, we have the jth element of the difference vector, the difference between w and the reference. And so if I have the jth element of one vector times the jth element of another vector summing over j, that's nothing more than the first vector transpose times the second. right? It's like we have a row vector and a column vector, and we know that when we do that matrix multiply, we have the first times first plus the second times the second, and third times third, and so on. That's exactly what's going on here. So that gives us this expression. So now we've gotten rid of our sums. We can see everything in terms of vectors. And then the last thing we can do is we can say, okay, if I want an approximation, I can get rid of this higher order term and change my equals to an approximately equals. And that gives us this. So we say that this is an approximation, and this is a good approximation for W near the reference point. And the last thing to do is just to write this in a slightly different way that's going to be able to make a direct comparison to what happens in the matrix case. And for that, we're going to use something called the inner product, something from linear algebra. So when we are dealing with real valued vectors, and you want to know what is the inner product between two vectors A and B, that's just going to be A transpose B. So when you deal in linear algebra in general, you talk about vector spaces, and vectors are actually very generic objects. They can be lists of numbers, like this, but actually you can build them much more generally. You can have matrices. Those are vectors in a vector space. You can have functions. Those are vectors in a vector space. There's all sorts of things you can do generically with vectors. And when you look at a particular kind of vector space called an inner product space, then you always have this notion of an inner product. And what the inner product tells you is it tells you a way to measure the angle between vectors in your space. So it's this kind of generic or abstract concept. So like if I give you two functions and I say, what's the angle between these two functions? You would say, okay, well, the inner product gives me a way to measure the angle between functions, and then I could define it. It would involve an integral and so on. And so here, when I have two vectors, and you ask what's the angle between two vectors, that's pretty easy to visualize, especially in 2 or 3 dimensions, right? You just plot the vectors, you look at the angle between them. And that's essentially what this inner product is measuring, is something like an angle. At least when you normalize it, it can give you something like an angle. So that's kind of the notion behind inner products and why they're useful and why they're defined. And as we'll see, when we write the inner product this way and then we look at the matrix case, we'll see that it can also be written as inner product, and it's a way of connecting all these different special cases together. Okay, so to conclude, what we have is we have an approximation that says that a function at an arbitrary point W is approximately equal to that function evaluated at a reference point plus the inner product between the gradient and the error vector. And this approximation is good anytime W is near that reference point. Okay. So it's a way of approximating a linear function in a neighborhood of the reference. Okay, so any questions on this slide? All right, so let's move. Oh, let's do a quick application of some of what we just developed here to understand a bit more about the gradient. So I told you before that the gradient tells us both the direction of maximum increase and the slope of a function. So let's prove this to ourselves, that in fact, yes, it does this. And let's see exactly how we can prove it. So here's a picture of what we're talking about in this case. So here is the function, j. This is a case of d equals 2. So we have, in one direction, this would be like W1, W2. Here is the reference point. I'll put an underline under W because this is a vector. vector W naught. And so if I want to measure, let's say, the height of the function at W naught, that would be the height of this point. Or maybe think about it as like that. And so what we would like to know in particular is if I look at this point right here, and I look at the function, at that point, what is the slope? What is the direction of maximum increase? So in which direction do I have to go this way so that I get the maximum increase? And also, what is the slope of, if I move along that particular direction, let's say I find it's this way, I'm moving along that direction, what is the slope? Exactly. So this is what we want to do. So what we're going to do to do this is we're going to look at direction u. So that means that we're going to be moving from the origin in a direction u. And u for us is going to be a vector of norm 1. So it's just a scaled vector. Sometimes people call this a direction vector. It's just a vector of norm 1. So the norm is not important. What's important is the direction it's pointing in. So let's move in that direction, but only a little bit. So we're gonna move epsilon times u. So we're going to take a small step. Okay, so maybe I'll move it up to here. So this is going to be epsilon, this point is going to be W naught plus epsilon times u. And what I'm going to look at here, this is kind of the classic way that we look at slope, right? This is rise over run. We look at, we take a small step away from the reference. In this case, it's e times u. And I look at how much has the function increased divided by how much have I moved. So I've moved in the direction, or I've moved e times u, but u is a norm 1 vector. So the norm of EU is, norm of epsilon u is just epsilon. Okay, so I have how much have I moved vertically, how much have I moved horizontally. Pictorially, I'm looking at this. How much have I moved vertically versus how much have I moved horizontally? And the ratio between those is the slope at that point. Is everybody with me on that? Okay, so here's where we get to use our gradient approximation. What we're going to do is we're going to rewrite this according to the expression that we derived a couple pages ago. Or maybe it was, actually I think it was, yeah, this is the last page. So this one here, this is j at the reference plus the gradient of j at the reference transpose times w minus the reference plus order, actually, hold on, I messed up the this part. So that I want to do w minus the reference, but w is this whole thing, and the reference is omega naught, or w naught. So w minus the reference is just going to be epsilon u. So this is epsilon u. And then the last thing is I want to do plus order of the norm of epsilon u squared. So that's what we got from the previous page. Okay, is everybody with me? So we can cancel some terms. We can cancel this one and this one. Another thing we can do is we can notice that the norm of EU vector u, epsilon u norm squared is just going to be epsilon squared. Because u is norm 1. And then so what we have after all this is we just have this plus order epsilon squared, which gives us this. Okay, so then we can do a little bit more canceling, we can cancel, because this inner product is just a linear operation, so basically we can pull the epsilon out, and then we can cancel the epsilon down there. So these two will cancel. And now we also have this second term to look at. So overall, this is going to be order epsilon. So this is going to be order, or maybe, order epsilon. And the final thing we would like to do is say what happens as epsilon grows small. We would like to know, really, if I shrink this and make a tiny triangle there, that will measure the slope at that point. Well, this first part, because we've canceled the epsilons, has no epsilon in it. So that's always going to be this. And then the second term, as epsilon goes to 0, this order term goes to 0, and we're left with just this. Okay, so what we figured out is that the slope here has this form: gradient at the reference point, transpose u, where u is a direction vector. So we're almost done. For this next part, actually, it may be easier to ignore these parentheses, okay, just based on the way that I describe it below. Okay, so what we can do is we can just rewrite this by sneaking in these two things. They will cancel, right? So I can put this on top and bottom. That's like multiplying by 1. And I can sneak this in the bottom because we know that the norm of u is 1. But the reason we're doing this is that now we can see that the second term is always going to be between 1 and minus 1. This is a consequence of Cauchy-Schwarz inequality, which says that anytime you have two vectors and you have this form like this, the answer is at most 1 and at least minus 1. And furthermore, and so that's why, if I think of this gradient as a and the u as b, then that's where we get this. So that means that our slope is somewhere between this norm and negative that norm. But we can go a little bit further and we can say, okay, we know that from Cauchy-Schwarz, the way to get the maximum value is to set b collinear to a. So they should be pointing in the same direction. So that means if I want to maximize my slope, I should pick my direction in line with the gradient. The direction should be in the gradient direction. Okay, so we've now learned two things. Number one, we learned that the maximum slope is the norm of the gradient. Number two, we learned that the direction of the maximum slope is the gradient direction. Okay, so that's just a proof of what we started out this unit saying, but now you can see with this gradient approximation exactly how we can derive that. Another interesting thing to point out is sometimes when we draw these pictures, we use contour plots. These are equal height contours of the function j. And one property is that the gradient at any point, the gradient, if you're looking at a contour point, is always going to be perpendicular to the contour. You always move perpendicular to the tangent of the contour. I think you could also see that back on this figure back here. The gradient is always going to be perpendicular to the contour. Okay, so we have our approximations of scalars and vectors, and we got to use our vector approximation to interpret the gradient. And the last thing to do along these lines is to consider the matrix case. So we have a matrix full of parameters. We have a function that takes in that matrix and returns a scalar, and we want to approximate that function at a reference point. In this case, the reference point is itself going to be a matrix. So when we do our first order Taylor series expansion, it's just a direct generalization of what we saw in the vector case, in the scalar case. Now we look at the partial derivatives with respect to all of our matrix elements. And we have to sum over all those elements, and for that reason we actually need two different sums, one over the j coordinate, one over the I coordinate. So this is the linear term. And then we have all the higher order terms collected together. And we're saying that they depend most strongly on the sum of quadratic terms. So here again, we're going to have a double sum over I and j, and we're going to have wij minus the reference point ij squared. So if you remember, that's what this Frobenius norm of a matrix is. It's just you sum the squares of all the values, take the square root, but then because we have the square here, that cancels the square root. Okay, so it's a nice extension of the vector case just to have two different sums. So now we would like again to write this in a way that allows us to make a comparison to what we did before. So first we want to write this middle term in terms of just matrices, no summations. So what we can first notice is that this term here is going to be the ijth component of the gradient matrix. And this term is the ijth component of this difference matrix. So we're summing with this double sum over both components. So we can go a little further. We can get rid of the sum, a couple more steps. So let's say we transpose this matrix. So I'm going to put a transpose here. And I'm going to swap these indices because I transpose it. So now we're going to have ji. Now let's focus on this interior sum over I. So we have one matrix on the left, another matrix on the right. I is indexing across the columns of the left matrix. I is indexing down the rows of the right matrix. And I'm doing a summation over I. Can you see that that's just a matrix multiply? So if I do this and I sum over I, it's like I'm doing this times this, and so on. And I'm doing this, and in particular, what I'm doing is I'm looking at the jth entry here, and I'm also looking at the jth entry here. So I'm looking at the same location on both sides, j and j. So what that's going to give me is it's going to give me this matrix here, evaluated at the jth row and jth column. That's what this thing is here. So if I have a matrix and I do a sum over the diagonal terms, that's all the jth row, jth column terms, there's a name for this. It's called the trace. So the trace is a sum of a matrix across its diagonal terms. So essentially what we figured out is that this whole thing is the trace of the first guy transpose times the second guy. Okay. Any questions on that last part? Okay, so a little bit of gymnastics there to see that. The very last thing is to note that this trace of one matrix transpose times another is actually the inner product for real valued matrices. So again, the inner product is a way that we can measure essentially something like the angle between things. And if you ask, like, how do I measure the angle between matrices? Well, the inner product is what you want to use. And then the question is, well, how do you even define the inner product for matrices? Well, the inner product is trace of the first transpose times the second. And another insightful way of looking at it is if you just write that out, it's like you're doing a pointwise multiply of the first times the second, and then you're summing over all the coordinates. So that turns out to be the, this is the inner product for real valued matrices. So what's nice about this is that at the end of the day, we have, we see that it's always the same expression, that you can write an approximation for a cost evaluated at W. W could be a matrix, it could be a vector, doesn't matter. And you're going to have the cost evaluated at the reference plus the inner product between the gradient and the error. So we saw that here. We saw exactly the same form here. It's just that the inner product adjusts to the shape of the matrix that you're working with. But otherwise, it's always the same. Okay, so these kind of approximations are useful anytime you are dealing with a matrix of parameters like we saw in multinomial logistic regression or linear regression with multiple targets. Okay. Okay, so we can do one more quick example where we look at an application of this, this last rule. So imagine that I have a function. Here's my generic function of a matrix of parameters, and I'm going to make it really nice and convenient. This function is just going to be sum vector A transpose times W times B. So clearly we have a row vector times a matrix times a column vector, and you carry that out and you get a scalar. And that's important because we need J to be scalar output. Okay, and if we want to expand this in terms of the summations, it looks like this. We could establish an index over A, we'll call it J, an index over B, we'll call that K, and then we do like sum across J times all the rows of W and the sum across K of all the columns of W, and this is how we do that vector matrix vector multiplication. Okay, so this is just relatively easy to work with. So the first thing we want to do is evaluate the gradient at the jkth entry of the gradient. So we know by definition that's going to be the partial derivative of J with respect to wjk. And if I look at this, so I have a double sum of many, many terms. But if I'm focusing on one particular jk, then only one of those terms in the sum is going to contain both the j and the k I am taking my derivative with respect to. So let's just call that single term this. Now we want to do the partial derivative of that with respect to wjk, right? That's pretty easy. Once I do that, I just get aj bk left. Okay, so we know that if I look at the jth row and kth column of the gradient, it's ajbk. So what is the entire gradient matrix? It's going to look like this. So this is J, this is my A, this is B transpose K, and this is going to give me a whole matrix. And if you think about what happens when I look at a particular value, a particular coordinate of A, particular coordinate of B transpose, that's going to give you a particular coordinate in this matrix. And that particular coordinate in the matrix is exactly this one. Okay, so finally, we have that our gradient matrix is this. Sometimes we call this an outer product of two vectors, it takes us into the matrix domain. Now, what's interesting about this, one thing interesting about this gradient is it does not even depend on W. The gradient is the same wherever you are. So, yeah, it's a constant. So, if we do a linear approximation of this function at a reference point W naught, we know that it always takes the form the function approximately equal to the function at the reference point plus the trace of the function, the trace of the gradient transposed times the difference from the reference point. So now we can plug in the gradient transposed. The gradient is AB transposed, so we have that thing transposed times this difference. The first simplification is we can distribute the transpose. So if I want to transpose product of two things, I swap their order and I transpose them individually. So we get this. And then we get, so I think everything is, and then this, for this term, we just evaluate this with W naught. Okay, so here's, the next step is one of the really cool properties of the trace. It's one of the main reasons why we like to use it if we can. If you have a product of two terms in your trace, you can swap their order. So as we know with matrices, in general, we cannot, they're not commutative. So we cannot say that BA equals AB, right? You know we cannot do that with, you can do that with scalars, but you cannot do that with matrices or vectors. But once you put them inside a trace, then you can. So, and here's one of the ways we can use this to our advantage. So we have this thing, which looks kind of like an unwieldy expression, but what I can do is I can actually move the B around to the back because it's in a trace. So then I get this expression. Now the next thing to notice is that this is actually just a scalar because I have a row vector times a matrix times a column vector. So it has this kind of form. It's a scalar. So the trace of a scalar is just the scalar itself. Because the trace is a sum of diagonal elements, and if all I have is a scalar, then there's only one diagonal element to sum, so I don't even need the trace there. So what I can do is I can remove the trace from the last expression, and I get this. And finally, you can see that we can cancel this term and this term, and that gives us that the function is approximately equal to this. Now actually, remembering what the function is, you can see that this approximation is actually perfect. It's a perfect approximation and it holds anywhere. And this is a consequence of the fact that we're applying a linear approximation to a function that is linear in W. So we expect the approximation to be perfect. But mainly this gave us a way of using some of these things and learning more about the trace. So we'll definitely use this trace trick more as the term goes on. All right, so any questions on this last derivation? All right, so let's take a look at doing this in Python. And we will learn one more important trick in Python here. So we would like to just evaluate this in Python. So there's a couple things to point out here. So in MATLAB, if you want to multiply matrices and vectors, you just use the asterisk. And if you want to do a pointwise multiplication, you have to use dot asterisk. Python is kind of opposite. If you want to do pointwise multiplication, you use the asterisk. And if you want to do matrix multiplication, then you can use this dot. So this is going to be W dot B is going to be this matrix W times B, And then the result of that, we're going to do another dot to get A. So this is how we can do it with matrices and vectors. So one thing I want to point out that's really important about, again, Python that is not true in MATLAB, is in MATLAB, MATLAB understands column vectors versus row vectors. Especially, you could say that everything in MATLAB is like a matrix. So a column vector is a matrix with one column, a row vector is a matrix with one row. So it just knows about those things. But in Python, when you talk about vectors in Python, it just thinks about it as a list of numbers. It has no concept of row or column because it's just a list. And so, so to do something like A, B transpose, in MATLAB, you could think of this as a matrix multiply. You're multiplying a matrix with one column times a matrix with one row, and you just use a matrix multiply. In Python, these are actually vectors. And vectors, there's no row or column vector. So this brings us to something called Python broadcasting. Super important concept. So if I want to do this A-B transpose in Python, or in NumPy, this is what I do. I first expand this vector A into a matrix. And I tell it, so the fact that I have two different coordinates here, first, second, means now I'm thinking about it as a matrix. And I'm saying build a matrix where the values in A are stored along the first dimension, so like this is a vertical column vector. And the second dimension just, there's no new information to add, so just think about that as a single dimension. So this guy we can think about as something like this. Now for B, we want to make this into a row vector. So we're again going to think about it as a matrix with two different coordinates, but I want the original values of B to go along the second coordinate. So the second one here, we're essentially like reshaping it into a row vector. And finally, once we've done that, then we can use the asterisk in Python, and it knows to do a column times a row vector, and it's going to give us an entire matrix. So this is a super useful trick. It shows up all the time in Python. If you didn't have this trick, you'd need to like build stuff in for loops. And when you write things in for loops, the code is very slow, especially as things get big. So this is a very fast way of implementing it in NumPy. So anyway, yeah, that's how we're doing this. We're implementing this part using these dots, and then we're implementing this using Python broadcasting. So you'll have some examples in the labs, but also there's a notebook way back in Unit 0. The Unit 0 notebook or demo on Python broadcasting. So there's several examples there. So over here, I was basically saying the same thing as on the right. So once we've programmed this function, we can just make, let's say, a 4x3 matrix. For W, A is going to have 4 columns. A is a vector with 4 entries. B is a vector with 3 entries. We evaluate our function, and we can print out the different things it returns. So J is a scalar, and then the gradient, you can see, is a 4x3 matrix. All right. So this is a good time to stop. Next time we'll talk about how to use the gradient to do optimization using gradient descent. For now, we learned all about the gradient, and that's enough. Any last questions? All right, have a great weekend, guys.